Hello, student. Uh, Welcome back to this topic of digital to analog conversion. In the last session, I have discussed the R to 2R binary ladder network regarding this digital to analog conversion. So we have mainly discussed only on the binary ladder network, but even though the digital to analog conversion takes place in the binary ladder network, it is not enough just having the binary ladder network to convert the digital to digital signal into analog signal. Lot of other components or other circuitry are required to convert a digital signal into an analog signal. So in this session, I am going to discuss a practical digital to analog converter, how it looks like, and what are the important uh, components or the parts of this digital to analog converter. So either the resistive divider or the ladder type of network can be used uh, as a basis for the digital to analog conversion. So it is in the resistive network that the actual translation from a digital signal to an analog signal or analog voltage takes place. So, but some other things are also needs to be done uh, uh, during the conversion of this digital to analog conversion. As an integral part of the digital to analog converter, there must be a register that can be used to store the digital information. So just having the, as I told, just having the binary ladder network or resistive divider network is not enough to convert a digital signal into analog signal. So there must be one register, means a memory, so that the digital information is stored. The simplest register is formed by the use of RS flip-flops with one flip-flop per bit. So the simplest register or the memory devices used here can be the RS flip-flops, and these flip-flops are used for every bit. There must also be level amplifiers between the register and the register network to ensure that the digital signals presented to the network are all of the same level and are constant. So these level amplifiers are also needed here because in digital electronics, they all use the binary logic, and the logic 0 means the 0 volt, and the logic 1 means the applied full voltage. So suppose that you are using a 10-volt battery as a supply voltage, and whether the 10-volt is there exactly in the signal when the level goes highs used to be checked. So that is why, for that reason, these level amplifiers are required. So these level amplifiers are inserted between the resistor, means the RS flip-flops, and the resistor network to ensure that the digital signal is presented to the network are all of the same level and are constant. Finally, there must be some form of gating on the input of the register such that the flip-flops can be set with the proper information from the digital system So a gating, there must be some form of gating, means the inputs to these registers are given through some gates. So the use of gates or gating system here is that they produces the output only when some logical conditions are verified at the input level. So because of that reason, these gating system is required before the that registers or the RF flip-flops. So that I will show you in the next circuit diagram. And so proper information from the digital system, a complete digital to analog converter in block diagram form is shown below. I will show the diagram. So two diagrams are there. So this is the complete digital to analog converter in a block diagram form, and these every blocks are expanded here in the figure B. So the block diagram of 4-bit digital to analog converter is shown in figure 1A and is expanded as shown in the figure B. It is clear from the figure 1B is that the register network is used is of the ladder type. So you can look at the figure B. So the resistor network used here at the end of this at the output level of this level amplifiers is R to 2R type ladder network is used here. But however, you can also use the resistor divider circuit also. So here ladder network is used. And next, the level amplifiers each have two inputs. One input is the plus 10 volt from the precision voltage source, and the other is from a flip-flop. The amplifiers work in such a way that when the input from a flip-flop is high, the output of the amplifier is at 10 volt, and when the input from the flip-flop is low, the output is 0 volt. So here I will show you in the circuit. So in this block diagram, digital inputs are given here. So input gates are there. Gates are there. So these are the input gates. A gating system is used here. So this gating system is required because the digital inputs will have to be satisfy some logical conditions. Then only the output is produced by these gates, and any one any one of this input will be on at a time. So actually, two inputs are given to this RS flip-flop. One is from this gate, another one is from this gate, but depending upon the logical conditions of these two gates, only one output is produced here, other will be at a 0 level. So that is how this gating system works. So here Reading strobe comes here, means the signals, digital signals are coming here. So these gates will check for the logical conditions to be satisfied, and accordingly they give the output. So that output goes into these RF flip-flops, and the information is stored in these registers. So you can see here, so this is the input gates and n-bit register. These are the n-bit register. That means right now it is shown for the 4-bit converter, but there can be n number of bits also. So n-bit register is there. And next, so these n-bit registers are made up of this RS flip-flops, because these RS flip-flops are simple memory devices and easy to work also. So RS flip-flops can be used here. Then these level amplifiers comes here. These are the level amplifiers. So these level amplifiers are present between this ladder network and these RS flip-flops. And these level amplifiers are having two inputs. One input is from this precision voltage source. It gives a voltage of 10 volt, and it is a precision voltage source because the output of this will be exactly 10 volt. And this 10 volt is given to these level amplifiers, and one signal is also coming from these RS flip-flops, and the voltage level means when the output of this RS flip-flop is high, it should be 10 volt. Whether it is 10 volt or not, that is checked by this level amplifier, because this level amplifier could be a comparative circuit which is constructed based on op amps. So these level amplifiers compare the output of this RS flip-flops with the reference voltage 10 volt, which is coming from this precision voltage source. And if it is not there, these level amplifiers correct it to 10 volt. That is why these are called as the level amplifiers. Then the output of these level amplifiers is given to finally these ladder network. And you can see here 2 raised to 0 input is coming in this way. So this is called as the LSB. This is LSB register, means low, that is the least significant bit. So this is the LSB side. This is the LSB side, and you can see here 2 raised to 3 is there. So the highest value of the bit is here. So this is the MSB. This is the MSB end, and this is the LSB end. These things are cleared. And the next, so when the input from the flip-flop is low, the output is 0, and the 4 flip-flops present in the circuit form the register necessary for storing the digital information. The flip-flop on the right represents the MSB, and the flip-flop on the left represents the LSB. Just now I told, because 2 raised to 0 in bit is here, so it is MSB, and 2 raised to 0 bit is here, so it is the LSB. Each flip-flop is a simple RS latch type and requires a positive level at the RRS input to reset or set it. So the gating scheme for entering information into the register is straightforward and could be understood easily. So as I told, the output of that gates will be high only when certain logical conditions are satisfied at the input level. So here with this particular gating scheme, the flip-flops need not be reset or set each time the new information is entered. So these RS flip-flops need not be reset because the resetting or setting of the flip-flops takes place according to the output of the uh, gates, which is fed into the RS flip-flops. When the reading line goes high, only one of the two gates outputs connected to each flip-flop is high, and the flip-flop is set or reset accordingly. So as I explained, when the information, digital information is given to all the logical gates, only one of the gate gives the output. So that is given to this RS flip-flop. Thus, the data are entered into the register each time the reading strobe information pulse occurs. And even D type of flip-flops could also be used in place of the RS flip-flops. So this is about this is about a practical digital to analog converter, how the circuit will be, complete circuit will be like this. And here I will explain how these digital to analog converters are tested, or how these digital to analog converters are checked. So two simple but important tests that can be performed to check the proper operation of these digital to analog converters are one is the steady state accuracy test, and another one is the monotonicity test. And these two tests can be conducted on the digital to analog converter to know its performance. So the steady state accuracy test involves setting a new digital number in the input register, measuring the analog output with an accurate meter, and comparing with the theoretical value. So in this way, we can check the steady state accuracy of the uh, digital to analog converter. Then how this monotonicity is checked? So checking for monotonicity means checking that the output voltage increases regularly as the input digital signal increases. This can be accomplished by using a counter. We have to use the counter as the digital input signal and observe the analog output signal on the oscilloscope. So so for proper monotonicity, the output waveform should be a perfect staircase waveform as shown in this figure. So this is the output of the digital to analog converter. It should be a perfect staircase like this. So the steps on the staircase waveform must be equally spaced and of the exact same amplitude. You see these are the steps. They should be equally spaced and there should not be any missings. And missing steps of different amplitude or steps in a downward fashion indicates some malfunctions. Suppose that means if the steps are of different amplitude and if some steps are missing, then we have to mean that this digital to analog converter is not working properly. So by conducting these two tests on the digital to analog converter, we can check its performance. So this is about practical digital to analog converter, and just go through it. Thank you for watching.